Hey, so my name is Brian Warner. I'm an engineer at Agoric. I'm going to be talking about a couple of different features of our platform. I'm going to go into reentrancy hazards and how to protect against them. I'll talk about access control mechanisms, and I'll go into the comms layer, the CLIS that we use to have the different machines in our system talk to each other. So let's dive right in. So we have good. Kate Sills has a good Medium post on this from about 2 years ago now, in which she is describing how to protect against reentrancy attacks in Ethereum in particular. So imagine that you have some simple little program that lets somebody buy a painting, and you check, buy a painting for $100. You check their balance, you call a customer provided function to deliver the painting to them, and then you deduct the balance. If you've done programming in Ethereum, you can already see the danger here. The kind of time of check to time of use sorts of problems. What we expect the user's delivery method to do looks something like this. In this kind of visual language here, this is supposed to represent the stack frames and the control flow. So control starts by entering into the buy painting function. It is going to do the balance check internally, and then it's calling out to this user-provided delivery function, which may have some subroutines, it may do some other stuff. And then we expect that that's just going to return normally, and then we can deduct the balance. So this is the kind of happy path, and if you're under pressure, you might only think about the happy path to make your stuff work. But the surprising path, the most obvious thing that the delivery function could do that would be surprising is to throw an exception. And that would bypass the extra work you're doing afterwards. It would fail to deduct the balance, and they would get the painting for free. The even more exciting, surprising thing that they could do is to have their delivery function call back into your buy painting function. Now you've got this nested check that you weren't planning for. And if they only started out with $100, they're going to get 2 paintings out of this, and you're going to wind up with some invariant violated, like they'll have a negative balance afterwards, because you didn't plan for this sub function to ever re-enter, to enter back into your buy painting function. My favorite example of this comes from Mark Miller's PhD thesis. He's our chief scientist. And there's just a simple publish subscribe example. The social contract of this is super simple. There's a set of subscribers. Somebody can add a subscriber to the set, they can remove a subscriber from the set, and they can publish a message to everybody in the set. And what's supposed to happen is that every time somebody publishes a message, every subscriber should get 1 copy of it in the order that it got published. I love this example because there's maybe 4 lines of actual code here, and there's at least 4 ways in which it can just explode. It's simple, it's easy to read, and it's horribly, horribly flawed. It kind of captures everything. If the user-provided update function were to throw an exception, then that would break this loop, and only half your subscribers would get the message. The other half wouldn't see anything because we'd have broken out of the loop. If that update function were to add a new subscriber, then does the new subscriber get the current message? Do they not get the current message? You're mutating in a set that you're actively iterating over. And the behavior of that depends upon the language that you're using. Something like Java is going to throw an exception. It doesn't let you mutate something while you're walking through it. Other languages may do something completely non-deterministic. JavaScript has a well-defined deterministic behavior here, but I don't happen to know what it is. And I'd argue that the person reading this code or auditing it shouldn't really have to know that either. If the user unsubscribes somebody or somebody else from there, you have the same sort of question. And then the reentrancy hazard is where the update function actually goes and publishes more data. And what's most likely to happen is that you get the first message gets sent out to half of the subscribers, then the second message gets sent out to all the subscribers, and then the first message gets sent out to the remaining half of the subscribers. And so that violates the contract that we have that says those should show up in order. So this code, there are ways to work around this. There are ways to protect yourself against this. You might make a copy of the subscriber set before you iterate over it to protect against mutation. You might put a try-catch around the update call to protect against exceptions that take place there. Or you might, in addition to those things, you might add a flag to say whether we're in the middle of doing a publish. And if somebody tries to publish while we're in the middle of publish, you queue their update, and then you service the queue after you come back from the whole thing. And so you can mitigate these hazards, but it would make this code at least 3 times as long as it is. It wouldn't fit on a slide anymore. And really, this code is kind of perfect as it stands, except for this fatal, horrible flaw. This code ought to work. But there's hope. With just 1 character, this code can be saved. Adding that little tilde in there changes that immediate send, the immediate call to the update, into an eventual send. And that makes this thing safe. Now, this syntax is kind of new. This tilde dot syntax is something that we've proposed to the ECMAScript committee to provide this eventual send operator in standard JavaScript. In Agoric code base, because the tilde dot syntax is not known by IDEs, editors would highlight this as a typo. In a lot of Agoric code, you'll see this other form with the E function, and this expands to the same thing. Both of these are roughly equivalent to the last line. What we're doing here is we're setting up a promise, and we're using the then method on it to take that call to the update function and push it off to sometime in the future. In JavaScript, this is called the microtask queue. This is using the event queue that's built into JavaScript in order to schedule work for some point in the future. This is another neat thing here is that the eventual send operator returns a promise for the result of whatever the update returned. So if you want to chain methods, you send one message and it gives you back a value, and you want to send another message to that second value, then you can chain these things together. So because eventual send returns a new promise for that result, if you don't need the intermediate result, you can chain these things together in a very concise, elegant syntax. This also enables a thing called promise pipelining that Michael alluded to in the last talk, where you can batch all of the messages going to a remote machine together into a single bundle rather than waiting for a round trip each time. If you don't need to wait for result 2 here, then you can send the more message early. You can say, I'm going to send you update, and whatever that returns, please send the second one to it. This is especially important when you're trying to collapse out the round trips that it takes to talk from the wallet machine to a chain, because every one of those messages when you're talking to a blockchain takes the full block time to get a round trip. So reducing your latency from n times 5 seconds to just 5 seconds is a really, really big win. So to contrast the two different kinds of invocation, the immediate call here would look like this. The publish method does some setup work, maybe call it begin. It's expected to do some stuff at the end, and then it calls each of these user-provided, attacker-provided update functions synchronously inline. The hazard, of course, is that any one of these update functions might throw an exception or might call back into publish or might do something else that surprises you. In the eventual send flow, it merely queues calls to this, and it pushes it onto the run queue, onto that microtask queue. And so later, after we've returned, then it finally goes and calls those update functions. And so nothing that update does can surprise us because we're not even running anymore. So the Agoric platform has a more generalized mechanism here, this run queue, that pushes all kinds of messages onto the queue. And this turns out to be a pretty distinctive feature. If you're familiar with the way that Ethereum works, then every message, every activity on the chain starts with a signed message, signed transaction that is broadcast to all of the miners. That the contract that message is delivered to has some internal subroutines, it can do some work there, and with the call opcode, it can call out to a different contract. But all of those other contracts are invoked synchronously. And the initial contract won't get control back until that one comes back. It can't do any more work until that subcontract has finished doing its thing. Now, Ethereum has some built-in protections against the subcontracts throwing an exception. If that causes the upper contract, unless the upper contract catches that one, then the entire transaction is unwound and all the stake is rolled back. But there's nothing in Ethereum to protect against reentrancy. And as we've seen, this has caused literally hundreds of millions of dollars to be lost, where somebody found a way to exploit a reentrancy bug in order to trick some contract into doing the wrong thing. So in the Agoric model, separate contracts can only communicate, can only interact with Eventual-Send. There is no synchronous calling from one contract to an unrelated one. In addition, the message that triggers execution might not come from some solo machine sending something with a public key. So there are a variety of events that can trigger this thing. And all of the wiring from one step to the next happens through promises. So in this example here, the contract tells, contract 1 tells contract 2 to do something. And by putting a then on that call to start, on that eventual send call to start, contract 1 will get control again once contract 2 is finished with its start. In contract 2, it's going to subcontract out to contract 3 and do some more work when that comes back. And because start is returning the contract, start as returning that promise, it means that contract 1 can wait for it. So all of these events are lined up. They're all happening on separate turns, so they're all safe against each other, doing surprising things. And this is how a lot of our platform is built. This enables a really interesting set of composition properties. So imagine that you have some external message, maybe from some wallet machine, that triggers a contract to open up and start working. The first thing the contract does is to start a timer and then also subscribe to a price oracle. And it wants to wait until the oracle subscription is complete before it's going to then announce itself as being ready. And maybe it tells the caller, okay, we're open for business now. And it just does that by hanging a callback, hanging a then off of the promise that it got back from oracle.subscribe. Later, the price oracle gets an update, and it notifies all of its subscribers to say, hey, here's the price update. And the contract can check the price, and maybe the price hasn't gone beyond some threshold. It doesn't need to do anything. This is going to ignore it. So the contract just returns, nothing special happens. And then even later, the timer fires. And the timer notifies the contract that time has passed. The contract says, oh, hey, that means that I have to expire now. Whatever we were going to do didn't happen within the expected time period. So we're going to close out now. It might notify the escrow property it should settle some stuff. When that finishes, it's going to trigger a done method. It'll tell its clients, hey, we're finished now. All of these different events are just pushed onto the same run queue. So not everything has to be triggered by an outside user calling it and doing something. So the run queue and the ability to use it for sending messages back and forth is a pretty fundamental property of our platform. I'll wrap up this part with a warning. In 2017, about 3 years after promises were added to JavaScript, the language acquired the async await syntax. This is a mechanism by which you can mark a function as always returning a promise, and from within that function, you can wait for other promises. You can effectively block execution until that is fired. This makes a lot of operations very easy to read, but it can reintroduce this reentrancy hazard. So in this example, suppose that we're logging this message after we send the delivery to deliver the painting, and we don't know we know it's not gotten there yet. So the message is delivery sent. It's not delivery complete. Now imagine that your product manager comes along and says, this message is kind of wishy-washy. I'd really like it if we could tell somebody that the delivery had actually succeeded and not merely that it was scheduled for the future. So somebody comes along and says, oh, hey, I know about this await thing. We will just not emit the log message until we've finished doing this delivery. And async await is a nice, elegant, readable way of doing this. But this resurrects the reentrancy hazard, because none of the code beyond this point is going to execute until after the user-provided deliver function has run. And as we saw before, that can do whatever it wants and can do something really surprising. The async here is fine. That's not causing any problems. It's this await call that's specifically causing the hazard. So if you choose to use await, the best way to think about it is that your function is split into multiple pieces at each await. If you have one await in your call, it's like you have two separate functions, the part before, the part after. And the second piece lives in this totally different world than the first. It gets to see the same variables, it can close over stuff from earlier in the function, but it can't rely upon any of the invariants, any of the status checks, any of the balance checks that took place there. It's a little bit like, you're sleepy, you're not going to fall asleep. No. You're just going to close your eyes just for a minute. And then you open your eyes again and you realize that you've completely fallen asleep. You don't know what time it is. You don't know what you've missed. That thing you put over there, maybe it's somebody moved it. You're in a different world. So if you use await, then kind of every time that you come back from the await, you need to reestablish whatever conditions you thought were present, because you were not in control the entire time. If you don't have await, then and you're only using Eventual-Send, then you know that you have not lost control at any point during that function. Okay, so next section is about access control. If you have a service, the service receives requests. Whoever designed the service has some idea about what requests are legitimate, which ones are attacks or somebody trying to access stuff that they're not supposed to. So access control in general entirely comes down to should this request be honored? And one of the very traditional methods of doing this is called the access control list, or the ACL. We call it an ACL. And this is usually expressed as a table. You've got a set of principals, which are parties that can do a thing. You have a table of permissions, which are things that could be done. And at the intersection at every cell of this table, there's a Boolean that says, is X allowed to do Y, yes or no? We're not really big fans of ACLs. And even in the best of times, we don't like them. But we think this pattern is particularly bad for smart contract systems. ACLs were developed back in the 60s on centralized computers where there was generally a single administrator that kind of managed this whole table. Whoever owned the computer, head of the department, whatever, was doling out these permissions. The columns, the permissions you can use here are pretty static because they refer to a fairly small number of fixed kernel APIs. It's not very dynamic. And this is a problem in smart contract systems because we want to keep innovating on new programs and new features that are there. And we want these features to be usable by others without prior arrangement. We don't want to have to go to some central administrator to say, hey, I built a new thing. Could you please allow people to use it? ACL systems also tend to assume that the principals are humans based on where they came from, kind of Unix file system sorts of things. And that would really limit composability because in our ideal system, a program should be able to do anything that a human can do. Any human should be able to delegate some of their power to an automated agent that'll do it for them. In ACL systems, delegation generally requires fairly special action by the administrator. You're creating a new principal, you're adding something to this table. Think about how on a Linux box in the file system, if you have a file that you can read and nobody else can read, how would you give one other user access to that? All the hoops you'd have to go through in order to delegate a single thing to a single other person. There are some ways of augmenting this system to enable better composition and delegation, but they tend to introduce new hazards like the confused deputy problem. So in our approach, we replace the principals, which were parties that could do a thing, with objects that could do a thing. And we replace the permissions, things that could be done, with objects, which when invoked, does the thing that could be done. And so then instead of focusing on this table full of Booleans, we focus on the references from the doer object to the doing object. And so instead of Alice being represented by an entry in a table with a bitmap that says yes for file X and no for file Y, Alice is an object that has a reference to file X and does not yet have a reference to file Y. In this kind of system, delegation is super easy. Alice can give Carol the ability to access file X by just sending a message to Carol and including that file X object as an argument in that message. It's also really clear that Alice can't give Carol anything that she didn't already have access to. Alice doesn't have access to file Y. She can't give it to Carol unless somebody else gives it to Alice first. And this is also super useful for reducing authority. So sometimes you want to delegate authority to a smaller portion of yourself. Standard software engineering practice says that you want to break up a big piece of code into smaller pieces that are easier to read, easier to reuse. And because permissions are just object references, we can invent a new permission by writing some code that wraps around an existing one and providing kind of a lower authority, lower powered form of access to that thing. And then we offer the new object to our subroutine instead of giving it the full powered one. Each wrapper that we write reduces the scope of that authority, and it's going to lead to safer code. So imagine that you have a program that is doing some sort of insurance contract. So you've got, the idea is that every day a weather report comes in. So I'm a farmer. I've purchased a security, an insurance contract that's supposed to pay out if the weather report indicates freezing temperatures and the crops get killed. So we presume that there's some big chunk of code here that is analyzing the weather report and figuring out whether it meets this criteria. This analyze weather report thing, if so the rules here are that if the weather report indicates this particular condition, then the client gets a payout, and it gets of a particular amount, and it only ever happens once per season, once per insurance contract, something like that. So this code's kind of straightforward. This is how you would imagine doing this kind of thing. There's a test, there's a flag to say whether we've done this once or not. And let's imagine that this analysis section is large and complex. It's got actuarial tables, it's got models about crop failures, all sorts of business logic. If you're doing it right, that should be like 90% of your program, because everything else is just boilerplate and glue logic. So all your business logic goes into this, and you're probably going to subcontract that out to some kind of farming weather insurance specialist that know this thing. Now, when your auditors come along and they ask for proof that this big chunk of code isn't going to go and steal your money, then that's a lot of code that they've got to examine. So if you kind of analyze the authority here, then everything inside this make insurance function has access to that purse, including all of the code inside that analyze weather function, and that's a big chunk of code. So you send this to your engineers, and you say, make this better. And of course, the first thing they do is refactor, right? What comes naturally is to move that complex logic out into a separate subroutine that has minimal inputs and minimal outputs. This function has one job. It's supposed to analyze the weather report and return a Boolean that says whether it meets these payout claims or not. This code has no business touching any money. So the fact that you can pass the weather report in here and not the purse makes it really obvious that this code has no business touching the money. It's not even being given the money. It doesn't have access to the purse. Then you make a second function, a utility function, to make sure the payout can only happen once. It's going to have a flag. It has the same kind of test it did before. This is the one that takes ownership of the purse. This is the one that knows what the claim amount is supposed to be, that is knows who the client is. The original purse is a fairly large authority. If somebody has access to the purse, then they can pay out as much as they want to as many parties as they want, as many times as they want. If you give them this thing instead, this payout once, this object with the payout once function method on it, then they're limited to only paying a particular client, only paying a particular claim amount, and only ever doing it once. So you've just taken this big authority and reduced it down to the minimal one that this particular application needs. So the phrase here is the principle of least authority. The idea is that every component of your system should only have the barest minimum of power, the barest minimum of authority that it needs to do its job and no more. And so when you've built those two utility functions, your top level code shrinks down to this kind of wiring. This is just wiring things up. And if you present this to an auditor, it's really obvious what it's going to do. There's a weather report. Every time it comes in, you analyze it, you maybe pay out. Done. The make payout once is such a common pattern that'll live in a well-audited library, so you're probably not even going to write that. The analyze weather thing is specialized code for your particular application, and that's where the bulk of the logic is, but it has minimal authority. The worst it can do is lie about or be incorrect about the claim payout. It does not have the ability to pay out things multiple times. This is exactly the same kind of pattern that our offer enforcement layer, our offer safety layer, uses to make sure that a contract can't do the wrong thing and can't cause the money to be lost entirely. The contracts are limited to choosing the layout, the arrangement of the assets at the end. So again, from kind of an insurance authority analysis point of view here, the analyze weather function no longer has access to this purse object. The amount of code that does is much smaller, and most of that is being managed by this payout once utility function, which is highly audited. So when your auditors come along, they don't have to look through all of that analyze weather code. They don't need to worry about whether that has a surreptitious payment call, and all the money you spend on the auditors can be spent having them analyze the business logic of analyze weather rather than trying to search through to figure out whether it's doing something surreptitious with the money. The fact that the analyze weather function wasn't giving any purses to spend from means it can't directly spend anything. Okay, so everything I've shown you here is up at the language level. All of the user code you're writing, all of the contract code you're writing gets to use all of the features that I've just described to you. But if you're familiar with Ethereum, if you're familiar with kind of lower level programming in these traditional blockchain environments, you might be wondering, where are the accounts? Where are the public keys? Where are the tables of contract addresses and stuff like that? I'll go into this a little bit. I can't get into a lot of detail in the time that we have. But the short answer is that those are all details of the communication layer that are hidden away from contract developers. And it's all hidden away behind the notion of a remote object, which allows everything up at this level where all of the programmers will be working to do everything, express everything in terms of object capabilities. So as a programmer, you just think about objects. If you have some objects in the wallet and they have a reference to some objects on the chain and some purses, in the back of your mind, you know that some of these objects live over here and some of these objects live over here. and those are separate machines, and something has to happen to get messages from one to the other. But that doesn't affect the way that you express how the send messages. The syntax is the same in either case. You're doing an eventual send. A is going to use the same syntax to invoke a method on B as B is going to use to invoke a method off on the chain, even though they live on separate machines. Now, behind the scenes, what's really happening here is that B has access, it doesn't have access to the object on the purse on the chain. Obviously, that's a different computer entirely. But it has access to this special proxy that we call a presence. And when B sends a message to this proxy, the target is looked up in a table called the C list, the capability list. All the details of this message are going to be serialized. We're going to keep track of who the target is, what the method name is that we're sending, what are the arguments, and it gets bundled into this data structure. Now, there's nothing in this data structure that says which object made the invocation, because object capability security is not so much about who you are, but about what you have access to. And so the C list has access to all the objects that the machine does, but any individual proxy will only ever put one target, one string, one object for into that message. So the proxies enforce the access control to make sure that B can't access something that B was not supposed to, and won't let the messages go to the wrong place. So those messages are bundled up with any other messages being sent to the same machine, and it's serialized into a bunch of bytes. And those bytes now need to be sent to this machine in a provable way. And this hands it off. So this layer was called CAP-TP, the Capability Transport Protocol. Once we have these bytes, we hand it off to a different layer called VAT-TP. And in the system, these are different VATs, and we're sending messages from one VAT to another. So this layer doesn't know what the bytes mean. It just knows that they have to get to that other machine, and we have to be able to prove to that other machine that they came from this machine. So this is entirely about transport. It's about provable sourcing of these things. And the way that this works depends upon the kinds of machines at either end. In this example, the wallet is a solo machine. It's running on your local computer. It's running on just one CPU. It's not a consensus mechanism. There's no voting. There's no blockchain there. But it's sending to a blockchain. It's sending to something like Cosmos SDK, which is what our platform is based upon. When a solo machine sends a message to a blockchain, it needs to be delivered as a signed transaction. It's going to be signed by a key that is held by the wallet machine as a whole. It's not any individual object on here. It's the machine talking to another machine. And this is a different layer of abstraction than the objects. So the VAT-TP layer in this case is going to take all of the bytes that it's been instructed to send to the chain. It's going to sign it with the wallet key, and it's going to broadcast it as a transaction. The miners, the validators on the chain will receive that. They'll check the signature. They'll deliver it to the VAT-TP and the CAP-TP layer on that receiving machine, and they'll say this came from a machine called wallet. That authorizes it to use this C list. And so when the wallet machine said, I want to send a message to object 4, the chain side machine can say, oh, when the wallet machine says it wants to talk to object 4, that really means this particular purse. And the wallet machine, no messages from the wallet machine are allowed to access anything that's not inside the C list. So this is now enforcing the fact that the machine as a whole can talk to this set of objects, and within that machine, some other mechanism decided it wanted to send something from to a particular object. So this whole mechanism is known as the comms layer, and this is completely transparent to contract code. Contract level code doesn't have a way to specify or even learn what these object IDs are. This is entirely a way of bridging two different machines to talk to each other, and to allow the receiving machine to figure out, okay, if the message came from this wallet, it uses this C list. If it came from that other machine, it uses this different C list that gives it access to a different set of objects. This mechanism is not specific to blockchains. This is a really generic mechanism, and we use it to get messages from any swing set-based VM, which is inside any kind of machine, to any other one. If the solo machine is sending a message into a chain, it's going to use a signed transaction like I just showed. If one chain sends a message to another chain, it's going to use IBC, the Inter-Blockchain Protocol, to emit a message that one chain will recognize as being valid, as being sent from another chain. When a chain wants to send a message down to a solo machine, it's going to emit a log entry that a light client on the solo machine can read and verify, and it can tell, oh, yep, that really did come from that particular machine. I'm willing to accept it. I'm willing to let it use things from the C list. And then when two solo machines talk to each other, because they don't have to have a consensus mechanism, they can just use regular TLS connections. They can use some kind of encrypted signed transport protocol. And so all four of these mechanisms appear the same way to CapTP. CapTP just says, hey, VATTP, please send this to machine X. And VATTP figures out, oh, right, you're a solo, they're a chain, I need to do this transaction thing. So all of this mechanism, like I said, is transparent to the upper layers. This is all about the mechanics of how systems work. But it means that all of your contract level code can work in terms of objects, in terms of object references, and doesn't need to, and in most cases doesn't even have access to things like keys, public key identifiers, contract A's, things like that. So that was a lot of material. Sorry I had to kind of rush through a lot of it, but there's a lot of stuff there. But the summary is, by using Eventual-Sends, you can avoid reentrancy attacks. By taking advantage of the run queue and by using object capabilities, you can reduce the amount of authority in any particular object. And all of that leads to a safer system. So thank you all for watching, and I'm really looking forward to seeing everything you do with the hackathon.
Thanks, Brian.